So, good afternoon, everyone. I'm Gaetano Cascini, full professor at Politecnico di Milano, Department of Mechanical Engineering, and I'm very pleased to join you in this session dedicated to model-based ergonomics. As in other sessions of this conference, unfortunately still virtual, we are going to attend 5 presentations delivered by playing a video. And then we will have the opportunity to discuss with the authors to maybe get some clarifications or to even enable maybe some discussion, some reflections, also maybe to find out possibilities to contact beyond the conference, because this is one of the things we like of the conferences. Getting new interactions and possibly collaborate in the future with some other colleagues. As I mentioned, 5 papers. I would say that this session is nicely focused. So indeed, the works are, really sharing several concepts, several relevant points. Specifically, we are going to attend the first paper presented by Alexander Wold for computer-aided ergonomics evaluation study of an interaction model for digital human models. The second one by Lewis Urquhart, synthesizing computational design methods for a human-centered design framework. Then by Sondre Johnston, pure vision-based motion tracking for data-driven design, a simple, flexible, and cost-effective approach for capturing static and dynamic interaction. Then fourth paper, Esteria Perez-Luque, challenges for the consideration of ergonomics in product development in the Swedish automotive industry, an interview study. And last but definitely not least, Sandro Wartzack presenting a musculoskeletal human model-based approach for evaluating support concepts of exoskeletons for selected use cases. Now, as I mentioned, I would like to play the videos one by one, but I warmly invite all of you to start posting questions or comments, whatever observations you like in the chat, paper by paper. We will collect them until the 5th paper has been presented, and then we will start discussing all of them. Later, once that all these 5 papers have been presented, I will be glad if others want to share the audio and video. But if we have at least an anticipation of the question in the chat, it would be easier to handle the order and to plan the discussion. That said, Fanica will help us. Thank you, Fanica, a lot for this great organization of the team in Zagreb. When you please, we can start with the first paper.
Welcome to our presentation. My name is Alexander Wolf. I'm a research assistant at the Friedrich-Alexander-Universität Erlangen-Nuremberg in Germany. And today I'm presenting you our paper, Computer-Aided Ergonomics, Evaluation Study of an Interaction Model for Digital Human Models. Megatrends like individualization, human-centered design are increasingly gaining importance in engineering design. In order to develop products more efficiently in a human-centered design way, digital human models like anthropometric human models or musculoskeletal models can be used. Those models can be used very well to virtually model different user group characteristics. The challenge, however, is to model the interaction between product and human. And therefore, we can use manual poster generation for anthropometric human models, for example, which unfortunately is very time-consuming and cumbersome, requires some sort of expertise, and has often questionable validity. For musculoskeletal human models, we have to go to the motion capture lab and capture the movement we want to investigate, fit them on the human models, which makes this process highly costly, time-consuming, and also a reaction or reactive approach. So in engineering design, we have the question, is there a more proactive way to synthesize and analyze human interaction behavior validly? To answer this question, we researched and developed a predictive interaction model embedded in a CAD environment, making use of musculoskeletal human models, and which is composed of 3 components. The first one is the catalog of elementary affordances. Affordance is an artificial term from cognition psychology, which describes possibilities of interaction with certain geometries. For example, a small and compact cylinder is more preferably contacted with a fingertip grip, whereas a long and slim cylinder is preferably contacted with a palm grip, as you can see here. We developed a catalog of 31 elementary affordances, where each of the affordances has a unique mechanical description. I don't want to go into detail here because we published this in the previous paper. The second part of the interaction model is the task modeling, where we developed a modeling framework in a CAD environment where the designer, or which allows the designer to define the interactions on a product using the affordance or the elementary affordances with so-called affordance features. I also don't want to go into detail here because we published this in another paper. What I want to talk about today is the prediction and analysis of the interaction behavior. Therefore, we use a method which I want to present to you now. This is how it works. On the one hand side, we have kinematic constraints described or defined in the CAD model using the affordance features, describing where the end effectors of the human model have to be. In a literature research, we found that this is not enough to describe or predict human behavior. We also have or need to use empirical data acquired through a one-time survey in order to characterize human behavior in this particular scenario. We describe them using behavior cards, which are made up from a posture described in joint angles and a coordination pattern, which describes the adjustment of those joint angles. In the next step, we can use a kinematic optimization to bring all together. We use the kinematic optimization to fit the posture from the empirical data into the kinematic constraints using the coordination pattern. And the question I want to answer or address today is whether the presented method is applicable to synthesize postures and evaluate product ergonomics proactively. Therefore, we take a look at a use case. In this case, we look at the stand of a dual rudder system of a yacht, which describes a whole body interaction with a certain complexity and relation to a real world problem, since the lever, which you can, the throttle lever, which you can see down here, is located just above the deck, which results in uncomfortable postures when maneuvering with the motor. In our study, we investigated 18 different scenarios of this use case by altering different product characteristics like the rudder position or the lever height, and also the lever depth. We did this on the one hand side with a subject study, where we had 5 subjects performing the same task for each product configuration, where we measured the postures and collected a subjective discomfort rating. After that, we fitted the measured postures onto our human models and analyzed them in a dynamic way. On the other side, we used our interaction model in order to analyze the scenario. First, we did a task modeling with our modeling framework in CAD. In a second step, we deduced the behavior cards from the empirical data by looking at the distributions or the patterns of the distributions of the different postures, and found out that it's a good way to represent or characterize the human behavior by using 3 behavior cards, 1 per lever height. After that, we use the kinematic constraints as well as the deduced behavior cards to predict the posture, which we analyzed consequently using the external forces you can see here. We use the same external forces for the dynamic analysis of the measured postures, so that we can compare the results afterwards. Now I want to show you the results. First, some qualitative results where we compare the measured posture on the left-hand side to the synthesized posture. And as you can see, they fit right or quite good, as they do for virtually all the postures we had in our study. A more quantitative way to compare it is using the whole body muscle activation, as you can see here. You see the different product configurations down here, and the whole body muscle activation of the experimentally measured postures against the predicted whole body muscle activation. The whole body muscle activation is the sum of all muscle activations needed to support the posture. So as you can see, the whole body muscle activation of the predicted postures is mostly within the range of the measured postures, within, while the measured or the experimental are far more spreaded. They have the same characteristic for all the combinations, as you can see, which is quite good. On the other hand, when comparing the whole body muscle activation to the subjective discomfort rating, which we did with the CP50 score, as you can see here, you see that it's also the same characteristic with respect to the combinations or configuration combinations, but there are a few flaws. For example, these points are clearly higher than those, which is not covered in our prediction data. So what can we learn from that? Our posture synthesis works since we could predict the same whole body muscle activations, and the postures look qualitatively the same. On the other hand, proactive ergonomics assessments seem to be possible, but certainly need improvement, especially when it comes to our assessment methods. Thank you very much, and I'm looking forward to your questions.
Great, thank you, Alexander. It was sure interesting, but we continue with Liu's presentation. Just a reminder, please post your questions or comments for Alexander in the chat. I will do the same. Thank you, Farika. We can go.
Hi, everyone. I'm Lewis Urquhart from the University of Strathclyde. And today I'll be presenting our paper titled Synthesizing Computational Design Methods for a Human-Centered Design Framework. So just to introduce the research, we seek to unify computational design methods with human-centered design methods to create a generalizable synthesis that can be utilized by practicing designers or researchers. So we're going to look at the following areas: a bit of background on computational design, and some of the applications, the examination of the different kinds of computational design, how they can be grouped, and how computational design tools can articulate with human-centered design methods for a generalizable synthesis. And we're going to look at some illustrative examples from the PrimeVR2 research project. So to start off, what is computational design? Computational design, in our understanding at least, is an umbrella term that encompasses a range of methods, including parametric design, generative design, and algorithmic design. So in general, these tools aim to expand the form-finding capabilities of designers and optimize spatial configurations around particular inputs and constraints. So optimization is a very important principle within these methods. The mathematical work in optimization done in the 70s and 80s was essentially combined with CAD, and this allowed new vistas of design to be explored. And well-known designers such as Oxman, Zaha Hadid, and Thomas Hellerich have recently all applied these kinds of methods in various ways in their own design work, pushing the boundaries essentially of strict optimizations and creating very interesting structures and interesting aesthetics. So while there are numerous examples of applications within art and architectures, as I've just shown, HCD and human factors are other areas that are receiving renewed attention. So in general, the principle of HCD is to fully enmesh perception, opinions, and experiences of potential human users within the design process, and creating products that are attuned to specific needs and specific contexts. So interesting work in biomedical engineering has explored this unification of HCD and design computation. So work by Abby Patterson, for example, has looked at the generation of bespoke injury splints that use an algorithmic workflow to generate the forms and incorporate anatomical scan data. So this is a nice unification of ergonomics and generative design principles and methods. So how did we create our framework based on some of this information? So by firstly exploring traditional design practices and traditional models of design, we define two broad levels by which computational design methods can be applied and integrated. So we call these the macro level and the micro level. So the macro level is the larger structural requirements, and the micro level is the detailing of finer design functions. So this was a framework that we ended up developing. So the start of the diagram over here is more aligned with the traditional design methods, specification and ideation, conceptualization. Over here is where we introduce the concepts of computation and the macro and micro realization outputs are based on computational coding and input parameters. So we'll just zero in on some of this here and look at this in a bit more detail. So the macro level, it will be quite familiar to many of you. So this is more about optimizing design solutions essentially without human factors concerned. So this is more about material saving and optimizing the spatial arrangements. So examples might be bridge construction or architectural design. Well-known tools like Abacus and Ansys are used in these macro level type computational design solutions. And by contrast, micro level might include more complicated data to do with human ergonomics, human interaction, human perception. And these outputs might be much more bespoke. So examples might be prosthetics, orthotics. And crucially, that here we can see that human factors analysis, that kind of data is integrated into the computational coding. So a set of tools that are possible to use in this way can be found in Rhino Grasshopper. There's lots of different plugins that can be used to generate this kind of design output, such as Pufferfish, Topos, Parakeet. There's lots of different things that can be explored. And indeed, the Prime VR2 research project has been using these tools in various ways. So at the macro level, we've been exploring the optimization of the large structural elements. So there's a component we're calling the wrist to elbow spine of our virtual reality wearable gaming controller. And we've done analysis in Ansys to optimize that form. And it has to consider complex pronation and supination movements of the arm. And also the micro level, we've been developing generative design algorithms within Rhino Grasshopper to achieve discrete functionalities and complex design detailing around wrist strap componentry, for example. So intelligence around ergonomics and tendon functionality, even aesthetics has been built into this algorithm to achieve this unique embodiment. So this is a nice integration of HCD and these general computational design principles. So in summary, this work is aimed to conceptually synthesize a range of design tools so they can be understood and applied by designers and researchers interested in the computational method. So our model presents a basis on which design problems can be approached at a macro and micro level in order to achieve stronger human factors of tuning. And we've given you a range of practical tools suitable for either the macro or micro level computational design problems. So thank you very much for listening. I'd be happy to take any questions at the end. Thank you.
Great, thank you, Luis. I see that some questions are appearing. I still warmly invite all participants to share their thoughts and questions, but let's move on with the next presentation. Thank you, Fanica.
Pure vision-based motion tracking for data-driven design. A simple, flexible, and cost-effective approach for capturing static and dynamic interactions. Hello, and welcome to our presentation. The paper presented is written by me, Martin Berg, Sindre Eikevåg, Sampsa Kohtala, Daniel Ege, and Martin Steinert. The article presents a series of experiments created to show use cases and implementation of the vision-based body tracking system, MediaPipe, in design of equipment and objects intended for human interaction. Capturing human-object interaction within design science enables designers to understand complex prototype interactions better. Capturing such data is not a trivial challenge, as many current technologies used for tracking interactions are expensive or lack the required fidelity. In this paper, we have focused on automatic systems for capturing human equipment interactions, as these can ease the data gathering process. There are three main categories in automatic body tracking: vision-based, reflector-based, and inertial sensor-based, of which the latter two technologies require the user to wear potentially intrusive sensors on their body during tracking and are confined to testing in lab environments. Vision-based body tracking has generally been regarded as lacking in fidelity, but we argue recent advances in open source software have increased both fidelity and accessibility for design researchers. With this, we present MediaPipe, an open source cross-platform body tracking software. MediaPipe functions by overlaying a skeletal model with 33 landmarks on the body of the subject and tracking these. Through pose estimation and shape feature prediction algorithms, it improves fidelity and reduces occlusion issues, which are both significant negatives in vision-based body tracking. Through two experiments, we test the vision-based body tracking system in different use cases. The aim of the first experiment is to analyze a user interacting with a keyboard in an office chair. This was done through a camera placed perpendicularly to a participant sitting in different positions. A study found that having a higher elbow in respect to the wrist position is related to positive comfort traits. With this in mind, the experiment was simplified to 3 positions with different indications on their impact on the participant. The positions are either with the elbow 5% higher than the wrist, indicated green, 5% lower than the wrist, indicated red, or in between, indicated in yellow. This graph shows how MediaPipe extracts the vertical coordinates of the elbow and wrist based on the height of the image frame. This method can be used to analyze posture continuously in natural settings, which can provide valuable insights that are difficult to measure in controlled lab settings. The graph shows the duration in which the user has a bad, moderate, and good posture according to the simplified criteria. The second experiment utilizes MediaPipe to perform a dynamic analysis of a participant rowing on a rowing ergometer in different seating positions. A prototype of an adjustable fixed rowing seat was created to allow for rapidly swapping both seat and back angles. The participant rowed for approximately 40 seconds in 3 different positions at a constant intensity for replicability. Stroke distances and body angles were extracted and analyzed by MediaPipe. The experiment was performed with 3 different camera angles, as seen in the figure, to also examine MediaPipe's reliability in between them. Note that the third camera angle was elevated 50% higher than the first 2. Afterwards, a measuring tape was attached to the handle, followed by a slower, more controlled exercise to compare MediaPipe to a ground truth given by the measuring tape. The next few figures show the correlation between the wrist movement during each position from the 3 different camera angles. MediaPipe shows a strong correlation between 96 and 98% between the well-behaving positions. Position 2 had an awkward occurrence in camera angle 3, but even then, the Pearson coefficient stays at a solid 80%. For the ground truth exercise, MediaPipe shows a very high correlation above 99%, with an initial root mean square error of about 65.5 millimeters. After fitting a simple linear regression model with only the second and third ground truth landmarks as guiding factors, the root mean square error was reduced to 28.5 millimeters. Furthermore, we can go on to show some use cases for design researchers. These graphs show the hip, elbow, and shoulder angles measured from the sagittal plane by MediaPipe throughout the exercise. Through body tracking, human motion dynamics can be analyzed to explain if there are irregularities in the human equipment interaction. For example, in the first position, the participant's maximum hip angle exceeds the seat angle by 19.3 degrees, suggesting that the seat's properties are prohibiting the user. Another discrepancy that can be seen is that the participant's furthest point forward is different between the 3 positions, even though the seat plate remains in the same position throughout all 3 tests. This could be caused by either 2 factors. The participant adjusted the horizontal position of the seat subjectively, which could impact his physiological ability to bend forwards. The other factor is the momentum carried by the participant from getting further behind in the movement, therefore gaining more velocity in the lunge forward. Body tracking can help both distinguish these differences as well as providing insight in potential causes. We have shown how media pipe can be used for post estimation in the context of design, demonstrating a simple, flexible, and cost-effective approach for gathering information for design researchers and product development. There are some additional uncertainties that need to be further explored, but due to its simplicity of only needing a sufficient recording device to interpret movement, media pipe and vision-based body tracking stands as the best candidate for following the athletes and users into their natural habitat during testing, as well as early implementation in the design and product development process. Thank you for listening.
Thank you, Sondre, as well. Very nice presentation. I see. Finally, we have questions appearing in the chat. Let's proceed with Estella then.
Hello, everyone. My name is Estella Perez-Luque. I am a PhD student at the University of Skövde in Sweden. And today I will present an interview study about the challenges of considering ergonomics in the Swedish automotive industry. Ergonomics designers are one of the groups in charge of studying how a product will affect the potential end user. Ergonomics design methods and objectives, therefore, can be applied in many different contexts or application areas. In this case, this study aims to understand the state of the art of how ergonomics is addressed in the vehicle development process within the Swedish automotive industry. Our aim is going to be divided into several objectives, identifying the ergonomics designers' objectives, their methods, tools, and the ideal tool for doing their work. In addition to that, we will also identify the main challenges that they have to face in their everyday work. When it comes to methodology, semi-structured interviews were used to gain a deeper insight and address the research aim. 10 ergonomics designers from 7 Swedish automotive companies participated in the interview study. The interview topics were specified following the objectives that I just mentioned in the introduction. And they consist in identifying the objectives, methods, tools, ideal tool, and challenges. The data analysis consisted of 4 steps. Data preparation, which covered the transcription of the recorded material, definition of the categories, data codification, and interpretation. Now I will cover different results briefly. The first phase of the interview focused on understanding their main goals. The interviewers answered these questions referring to the term balance and finding a balance between different things. The process of balancing mainly involves identifying specific limits of specific requirements, and also rank the importance of these different requirements. We have divided this balance into internal and external. Internal balancing covers several ergonomics aspects, finding this balance among ergonomics aspects, and they can be, for example, visibility, reachability, or roominess of the cabin of a vehicle. And in contrast, the external balance covers ergonomics with non-ergonomics aspects of product development as design or aesthetics. When it comes to the workflow, which is the second phase of the interview, here we can see a figure that represents a characterization of a typical ergonomics designer's workflow. This characterization is based on the interviews and their interviewers' answer. This workflow describes the steps of ergonomics designers through the different product design phases, where the most relevant steps are the internal and the external balancing. The third phase consisted in identifying all the different tools that they use. And here we can see some of the reported ones. In the paper, you can find a description and you can see the frequency of answers. The interview continued with a focus on identifying the key features of an ideal tool for the ergonomics designer. The main features that they mention is the easy to use, the usability of such an ideal tool, and the consideration of human anthropometry. Interviewers also visualize this ideal tool in two different ways. One of them is as a DHM software, but this digital human modeling software will have to improve some features as the usability or the predictions. And other interviewers saw this ideal tool as a virtual reality, augmented reality, or mixed reality, a tool that will allow them to combine the physical and the digital models at the same time. In the last part, the ergonomics designer will also ask about the different issues or challenges that they have to face. These challenges were divided into two different groups, and both of them affect the workflow of the product development. Some of them refer to tool development issues as bad predictions, lack of evaluation methods, or communication issues with other departments, or reporting the conclusions of the ergonomics balancing in this case. And to conclude, based on the interviews, we identify 4 gaps or research directions that could improve the ergonomics designer works. Those are improving human behavior predictions, the simulation tools, usability, ergonomics evaluation methods, and the integration between different tools, such as digital human modeling, CAD software, virtual reality, and so on. While addressing these challenges is no small task, we hope that understanding what challenges ergonomics designers face can shape and direct future research and development of digital human modeling tools and other design tools to support the development of more ergonomics design effectively. Thank you very much for listening.
Professor, please just unmute yourself.
Thank you. Thank you, Fanica. So, well, I was just thanking again Estela for the presentation, and we can go with the 5th presentation by Professor Wartzack.
Hello, everybody, and welcome to my presentation with the title, A Musculoskeletal Human Model-Based Approach for Evaluating Support Concepts of Exoskeletons for Selected Use Cases. My name is Sandro Wartzack, and I'm full professor at the Engineering Design Lab of FAU, and I'm happy to present the topic on behalf of the whole team. The publication is based on a collaboration between 3 institutes, and that are the Laboratory of Production Engineering at the Faculty of Mechanical Engineering at Helmut Schmidt University in Hamburg, the Institute of Product Engineering at Karlsruhe Institute of Technology, and the Engineering Design Lab at FAU Erlangen-Nürnberg. And the whole project is sponsored by the German Research Association. Some words concerning the motivation. The paper is about the design and optimization of exoskeletons. There's a high potential in the use of exoskeletons to reduce work-related musculoskeletal disorders. And there are different possibilities to develop, analyze, and evaluate exoskeletons. You can do user studies with various prototypes, or you can use digital human models. However, these digital studies often consider already developed design concept of exoskeletons, or the support provided by the exoskeleton is represented in such a simplified way, and that makes it very difficult to derive concrete design changes. Consequently, we present an approach for identifying the physical stress in the digital user in a selected use case on one side. And on the other side, we are evaluating potential support concept in the pre-design phase by using biomechanical simulation. Here in this slide, you can see our approach for the evaluation of support concepts of exoskeletons. And yes, it's a 5-step approach. In step 1, we start with the selection of the use case. In this case, it's a screwing task of a worker above his head. And we are choosing the setup of the biomechanical measurement. In step 2, we are performing the biomechanical simulation using musculoskeletal human models. And we analyze the load situation based on the use case. In step 3, first we identify the support demand based on the selected use case. Then we define the support concepts in the form of external forces. In step 4, we are concentrating on the selected support concepts and perform the mechanical simulation. And yes, you can imagine that the analysis of the support concepts affect the human body. And last but not least, we adapt and optimize the design of the promising support tools. This is our new approach. Now we want to concentrate on the different steps, and we start with step number 1, the selection of the use case and biomechanical measurement. Yes, we selected for this study a special task, a man, a worker who is working at and above head. Let me show you a short video clip, and this is realized by attaching small wooden blocks to a board above the subject, and the user is using a cordless screwdriver. The biomechanical measurement, on one hand, it's a motion capturing system with an optical system. On the other hand, we detect the muscle activation by using surface EMGs, and we detect the ground reaction forces by using force plates. And now we want to transfer this information to a musculoskeletal human model because we want to analyze the load situation in the use case. This is what we do in step 2. In addition to the movement, force generated by the applications are also introduced. And for this purpose, a constant weight force of the cordless screwdriver and a constant process force during the screwing in process are applied to the right hand. The resulting muscle activation will be compared to the measured muscle activation and especially examined for the loading situation during the load case. We are using the right deltoid muscle as an example. This shows the activation of the muscle increases, especially during the screwing in process, which could be used as a basis for possible approaches to relieve the user. In step 3, based on the analyzed load situation, various support concepts could be developed. Here, the support of the user is defined as a simplified force on the body part of the human model. And this allows the analysis of the effect of this support initially without further design changes of this support system. In the concept of the paper, 5 different support concepts are considered. Support concept 1 applies a force to the upper arm, which could be dependent on the movement or on the load. Support concept 2 adds a constant force to the forearm. And support concept 3 adds a constant force or a load-depending force to the hand. The potential impact of the support concepts can subsequently be analyzed using musculoskeletal simulation in the next step. In step 4, the effects of the different support concepts on humans are analyzed and also compared in relation to the base case without support. Here again, the example of the deltoid muscle is shown, and you see that concept support concept 3B was the best support. This is the light blue curve you can see here in this graphic. For a more comprehensive evaluation, other muscles and joints should be considered as well. And in step 5, based on the results of the biomechanical analysis, promising concepts could be considered in more detail, and concrete design concepts and prototypes can be elaborated, and further studies and analysis can be performed. Now I want to close with a short summary of the potentials and the limits. So what is positive? We have a support method for early product development phases by using simulations, low cost and time saving by reducing the need for increased product development, and the measurement effort is quite low for the experimental data. But we have also some limitations. For example, that the interaction of the human with exoskeleton and power tool is only present as an external force, and the reaction forces are quite simplified. The external force is considered optimal only in y direction, and there's no change in motion due to external forces. My conclusion is it's a promising approach to incorporate biomechanical simulation very early in the product development process. And I think we have to continue our work and have to implement the method for further use cases. Thank you very much for your attention.
Very, very nice. Thank you, Sandro. And well, by the way, it's not a chance. It also received the reviewers' favorite recognition. So congratulations for that, of course, to you and all the others. That said, well, I would like to start again from the first paper. We have a number of questions, and we can dedicate some 5 minutes to each of the presenters to respond to these questions. I'm happy to read them, but as far as questions come from either the presenters or other people in the room, in the virtual room, I'm happy if you ask to join us with voice and camera so that you can deliver the question directly, maybe more effective. Okay, so going back to Alexander, maybe Luis, you want to start? Your question to Alexander.
Yeah, sorry, I just thought, yeah, that was it. I was just wondering what the, I like the analysis looked like interesting and all, but I was just wondering this whole posture thing, how, to what extent was, your consideration also, to what extent was demographic also involved in the analysis? Because, I mean, the posture of someone, say, in their 70s is going to be different to someone who's 20. You may have mentioned that, but I didn't see it in the analysis. So I was wondering if you could comment on that.
And maybe, Alexander, if you allow me, to a certain extent, it is related to what I was asking, because I was asking whether you were involving several subjects or just one. Mm-hmm. This might be one way to explain the larger variability in the experimental results, but maybe there are some other reasons. So you can share your thoughts on this.
Yes, thank you for your very good questions, because we're very deep in the problems we have here. And this is the characterization of human behavior. How can we predict cognition? How can we predict what humans will do, what behavior is to be expected from them? And what we do in this approach is using a data-driven approach via those behavior cards I mentioned, which essentially come from empirical data. And in this study, we solely could measure 5 subjects due to COVID pandemic, unfortunately. We wanted to have more persons and participants in our study. And surely if we had a more diverse subject group from different age, different gender, and we had five male persons all around the age of 25 to 30, which is not that diverse after all. we would have get much more diverse postures, and we maybe would have used more or had to use more behavior cards to characterize human behavior. So this is a limitation of the study, and would have been or would be a really, really interesting point for the future.
On this point, I'm very ignorant, I would say, but what is a reasonable sample to, to say that for a given group of people, as you say, a certain range of ages, male, female, and so forth, you have a sufficient characterization?
I think this is different from use case to use case. I think the methodology we showed here is applicable for research institutes for specific use cases, but also for the industry for specific use cases. Let's take the yacht industry, for example. They know their user group, and they, in this case, we would need to test all the people which are relevant in this group, which are young people, which are also older people from different which have different characteristics. So you would really have to investigate a huge user group in this case, and afterwards derive the human behavior in this case with the behavior cards we used. And this would require a quite big experimental setup, but it would require to do the setup in a one-time expenditure, and after that we could use it in a predictive way. But the first time it would be a huge group of, I would say, at least 30 to 50 persons or subjects, yes.
Thanks a lot. I don't know whether there are other participants who want to make a question to Alexander.
Yes, I will have a couple of questions, if I can go. Yes. You mentioned the affordances, and you focus especially in the grasp. So you model different types of grasp as the affordances that the mannequin could do. But do you consider to expand your model also to consider different affordances, like visibility, like looking at a point, because that's another type of interaction. For example, physical interaction, I would say. So would you like to expand?
Yeah.
Thank you, Estela. Actually, it is a very important question, and I was more or less on the same page. So I'm very curious.
Yeah, that's a really interesting question. So affordance is a huge field. So for our application, we used the concept of affordances and boiled it a bit down, so to say. So we use it to describe basic interactions between rudimental geometric shapes like surfaces or cylinders or cuboids, and human end effectors like hands or feet or buttock and so on. So we have considered a lot of affordances which are interesting in the context of human-machine interaction, which also is looking at a certain point, or sitting on a chair, or leaning against the wall. So this is all involved, but on a very rudimental level. So you can say we have a surface, and the surface affords to sit on it, or to lean against it, or push your hands against it. So in this case, the user of the tool or the designer have to decide what do I want to, which affordance should I address to the surface for my particular interaction point on the product. This is a thing the designer still has to do, but our affordance catalog covers the most important interactions with machines. So also looking and so on, yes.
Yeah.
Okay.
And thank you very much for your question, for your answer. And also you mentioned here you model the postures, but have you think about expanding to motions, like, or how would you like to approach this? Yeah, because it's quite complicated, actually.
It is, so, yes. As you found out in your study, which is quite interesting for me, human behavior is one big point we have to understand, and we have to do a lot more research in. And I think you would agree with, if I say human behavior when looking at movements are much more complex to describe and to predict than postures. So for this reason, we focused on postures, since we have a better chance to characterize human behavior when looking on postures. And expanding this in a general way, like we aim to do with this approach with movements, is very, very complex and needs a lot more research. Still, postures will need much more empirical data and research. So I think movements would be much more complicated and is more of a vision than graspable at the moment.
Thank you.
Okay, good. So thank you, Alexander. I would move to the second speaker.
Thank you very much for your great questions.
Which is Lewis, and maybe I would ask Sandro whether you'd like to start with your question, Sandro. So Lewis.
Yes, thank you very much, Gaetano. I was wondering, how do you take into account the shape of the body parts? I think I did not get this information.
So yeah, and I mean, I didn't go into it in a huge amount of detail. This is true, but in the kind of work that we kind of based the model development on, which is the work from the Prime VR project that I'm involved with, we use a system of biomechanical scanning. So in our system, we're using an array of real sense scanners and also leap motion scanners to create a biomechanical profile that like contains this kind of ergonomic data. So we've got data on the geometry of the user's body, and also got data on how the user will move. And in our project, we're focusing on the arm and hand. So we scan that area. But yeah, does that kind of roughly answer your question?
Okay, so it was kind of scanning. I just got this information, but I didn't get this information in the presentation. Okay, thank you very much.
Yeah.
Thank you, Lewis. Again, I wonder whether there's anyone who would like to make a question to Lewis. Otherwise, I will proceed with the other one that was in the chat. Well, I can, since I wrote it. I was curious to understand a bit more your distinction between what you call macro and micro solutions or tasks. Well, you say solutions, but before, I mean, it's a distinction. And because you, in the slide, you showed us a distinction of tools that you suggest for each of those. And I didn't fully understand what was the rationale for this classification. I mean, because my impression is that you might use finite element analysis tools like Haukås or ANSYS also at micro level, and the other way around, machine learning at macro level. So maybe you can let us understand better what is this distinction about.
Yeah, I mean, I think you're sort of answering your own question in that statement that you just gave, whereby you could potentially sort of flip them around. So I wouldn't say the distinction is like a kind of a sort of rigidly logical distinction, but it's more of a kind of pragmatic it's a kind of pragmatic model that we came up with based on kind of our experience with using these tools. So we in the project I was talking about in the examples in the presentation, we used these we found that these kind of macro level tools that we're calling them, the sort of larger structural analytics, were much more useful at that, at that wider structural level than the tools that were, tools that are designed to configure, these form finding kind of computational tools, that can create kind of more intricate designs at a more small micro level. So it was a kind of pragmatic distinction on that level. But I agree that, you know, there is, it's not like a very rigid, hard distinction. Like you can, you know, you can use what we're calling micro tools at a macro level. But I suppose we would argue that in the main, it's more appropriate to use these certain tools at, you know, designing at a certain scale, I suppose.
Yeah. I mean, I think that the distinction was quite clear in terms of what was the scope of each of them, but less clear why certain tools are connected only to one category. That was the origin. But now,
yeah, I mean, it's kind of, I maybe should have made that clear. Yeah, so it was sort of drawn out of our own kind of practical experience using these tools, and that was the kind of rationale for the model.
I see. Okay, thank you. I would move to the third presenter, Sondre. Maybe Alexander, you can make your question, but before, allow me to just to ask a clarification one to Sondre. I understand it properly that MediaPipe is something open source. So maybe it might be nice if you share with all participants, not now, I mean, after responding, a link so that people can maybe enter and have a closer look into it. I mean, let's use this opportunity. But again, not now. I would say that now we can listen to Alexander's question.
Oh, of course, I would just like to preface also that with MediaPipe, I often refer to MediaPipe quite specifically, but for the points I was making, I often, or in hindsight, would have talked more about vision-based body tracking as a whole, where MediaPipe is more so a vessel of indicating how it functions.
Yeah, okay, I see. Thank you. Alexander.
Yes, my question is regarding the joint angle errors that are to expect when using video body tracking. So we know IMU and IMU is not that good as using optical marker tracking, and video body tracking is expected to be the worst of those three. But it's truly interesting, for example, to what we had in my questions before, characterize human behavior. What errors are to expect when using video body tracking? And yeah, did you compare it to the gold standard of optical marker tracking?
We did not get to compare it. I have other people on the faculty who have done the same tests with optical marker tracking, and it replicates it or in behavior. But that also comes to a later question, which is that it is also in rowing, which is predictable in a sense. Joint angle errors are obviously, there are a few different parameters that can affect how the tracking becomes. You obviously have things like contrast and lighting and frame rate, for example, which also comes in a later question. We found it to be in the tests that are presented, it is quite reliable. You can expect some errors, and in the tests that were off, in a sense, I described two tests that were awkward from the second angle in position 2, where from the side I had black sweatbands on, in which from the side the frame doesn't, or the software does not manage to differentiate the knee from the hip, which makes it quite a large discrepancy. So there are a few different errors to expect, such as that. I'd also like to preface a bit that a large part, which is not understood through the presentation, is that the paper in Nature is also very related to showcasing what vision-based body tracking, how much of an impact it can have if you can implement it or have a reliable vision-based tracking system that can be implemented. Yeah,
now I understand it better. I admit that I partially misinterpreted in the video presentation. Again, I don't know whether there are other participants who want to maybe make a direct question. Otherwise, I was just wondering whether you could provide more details on the specific system you were adopting. I mean, vision-based motion tracking. I mean, about the relationship between the working volume and maybe the resolution one would like to get, or even, I mean, we saw in the experiments you presented that they were mostly planar motions, but maybe, I mean, of course, it would be interesting to see even a purely three-dimensional situation. And also maybe something about the setup, whether any specific calibration is needed at the beginning.
Yes, so for working volume, a very nice, or we did not have any problems with like in resolution specific for a single camera in any way. There are a few specifics in terms of like it doesn't operate, or it does operate above 30 frames per second, but it does not get better above 30 frames per second. It does not register the frames. It can use cameras that have more than 30 frames per second, but it does not use the extra frames in a sense. Either that or through post-processing, it will simply double the time you need to process. So it basically does it in slow motion and makes it 30 frames per second. For complex 3D movements, that's a bit more intricate. We have not delved too much into it due to the nature of the research we are making, which is mainly on para-based rowing. But the 3 camera angles, and especially the third one with a 50% increase in height, are meant to represent a more, or how it would operate through a more three-dimensional movement. And as seen, at least for patterns, it to a high degree is replicable between the 3 angles, or between the angles. And as for details on how the setup works, it is not complicated at all. You can do it in post-processing from simply having a film. So what we would do, or for the initial version of the paper, we had taken stationary photos with a mobile phone and videos. So you can simply use a mobile phone, and then in post-processing through Python or through whatever coding you are using, you can simply add add media pipe and just read the body tracking.
Okay, thank you, Sondre. And I would move to the 4th presenter, Estela. Let's see. I don't know whether I see. Let's start with another participant. Please allow me, Sandro. So, Camilla, I don't know whether you are connected also with audio. Otherwise, I can read the question. Do ergonomics designers face conflict of ideas often with industrial designers? For instance, comfort issues versus aesthetics. And if so, how are they dealt by management?
Well, you can hear me, right?
Yep.
More than a conflict of ideas, I will say it's a conflict of prioritization, because I explained about the balance, the internal and the external balance. They have some requirements that they have to fulfill and so on. But when you go to the external balance, you also have to include the requirements from other departments, and then they prioritize all their objectives more. So there you find a conflict. And actually, that was one of the challenges that they reported the most, because they felt like they have to be continuously convincing people that the ergonomics is an important thing, and the designers need to adjust the design of the model of the vehicles to different anthropometries. So maybe for a small female, it doesn't fit that well if the design is, I don't know, if a button is in a specific place. So they deal a lot with this kind of issues. So yeah.
And related to this, still Camilla asks, do ergonomics designers work along with user researchers, marketing side team in some organizations, to back their findings with DHM software in the companies you interviewed?
With user researchers, like, I don't understand.
I mean, with people from the marketing, or for those who are studying
yes.
the users?
Yeah, in my interview studies, I consider people in different positions in the company. So some of them were specialists, were the people doing the simulations, but I also interviewed some managers. In the case of the managers, they mentioned that sometimes they are part of the marketing, when in the marketing team, when they define these requirements for a new product or a new vehicle, but most of the work is done later. So they are not always in this marketing, giving their ideas and so on. Sometimes they are just given, okay, you have to get this product with these specific conditions or limitations. So yeah.
Okay, good. Maybe Alexander, you want to make your question?
Yes, thank you. I did wonder whether the interviewed experts specify which parts of human behavior they are particularly interested in. So is it the traditional things like movements, postures, or is it also cognitive aspects? And are there concrete approaches in the industry to characterize human behavior? So to say with empirical data in their labs or comparable?
Yeah, exactly. That's how they do it. The people that I was talking with, they were having a lot of problems with the initial posture. So they are people dealing with the design of the occupant packaging. So the initial posture of the mannequin sitting in the driver's seat, that's problematic. And that's really difficult to adjust because it relies a lot in subjectivity. So each DHM user will modify the posture of the mannequin, but the adjustments that I do will be different than the ones that you do because it's subjectivity. So then they complain a lot about that they will like to have some methods, more I don't know, stronger methods to get more repeatable results at the end. And after that they need this initial posture in order to also evaluate the motions, because if you don't have the initial posture well enough, so then the rest, it's a bit, you cannot trust it 100%. So, and how they validate all this work is doing user tests. So yeah, it takes a lot of time.
Yeah. I can imagine. Okay, Sandro, there was a question of yours labeled P4. Was it about P4 or something else?
So I wanted to know concerning presentation number 4, because I understood that you want to predict forces, and I saw that you are using anthropometric human models. So how is it possible? Because we are using biomechanical musculoskeletal models, and we are able to predict forces for example, muscle forces or joint forces. What kind of forces are you measuring?
I wonder whether this was about paper 4 or paper 3, maybe.
4, paper 4, Estrella.
For me?
Yeah, that was for you. But anyway.
But the predictive forces, sorry, can you repeat? I was...
Only a short question. I read that you are predicting forces, and I saw that you are using anthropometric models, human models. And what kind of forces are you analyzing?
No, but my study was about the interview.
Maybe I would say that there might be some misunderstanding, but still, I mean, if it is not like this, you can possibly follow up after the session. While I will leave the last 5 minutes to address questions related to the 5th paper, also as a reviewer's favorite. So maybe Lewis, you want to start with a question to Sandro?
Yeah, so you said sort of at the end, and I thought, you know, some of the work looked really interesting. But you said at the end you want to maybe look at other use cases, you know, to explore this method in other types of activities. So I was wondering what other things might you explore, and then I thought, I mean, could there be some kind of activity or some kind of setup where you are able to provide a sort of useful ergonomic profile that could tell you about multiple kinds of devices or products and how they can be used ergonomically, if you see what I mean.
So in our project, I want to tell you the background from the project. So we are cooperating with Karlsruhe and Hamburg, and it's especially about exoskeletons for users who are using power tools, because my colleague Sven Matthiesen, he's researching on power tools. The colleague from Hamburg, Robert Weidner, is researching on exoskeletons. And the aim of the project was to support the workers in industry which are using power tools. But right now, it's possible with our approach even to support other systems, any support systems or systems technology or healthcare products, for example, or thesis, for example, could be supported by our approach, I think. But especially we are coming from the power tool and workers scenario.
Yeah, so like in the study, I mean, you had the handheld drill, right?
Yeah.
Have you explored other kinds of power tools yet? Have you just done just the drill so far?
Yes, so we can transfer to other tools, to our power tools, the screwers or other machines, but we can also transfer our technology, our approach to other support systems, even for thesis in the healthcare sector.
Mm-hmm.
And it's not the focus of the project, but that should be possible.
Mm-hmm. Nice.
Maybe Sandro, allow me also another question. I mean, the process is very clear, and it is really visible what kind of support you provide to each step. It was a bit less evident to me what is your actual suggestion at step 3. So when one want to define the new concepts. I mean, you presented nice examples, but I was wondering what kind of support can you give in that phase? Are you, for instance, having a kind of catalog of typical solution?
No, I am. No, we don't have. We are a team of around 6 to 8 persons, specialists, and we are working very much in team, and we're trying out and discussing many examples how we could support the worker, and it's done by brainstorming and so on.
Okay. Yeah, because maybe since you are categorizing so precisely the different postures, maybe one day it will be also possible to give some suggestions. Look, in these cases, it might work well. At least the area where to work.
This could be interesting, yeah.
Okay, I don't know whether there are any final remarks. I see that Sondre added the link to the console they use. Thank you, Sondre. And I think that we had a nice panel of presentations, also some nice questions and answers. I hope all participants enjoyed it. I still invite all of you to stay in contact. Maybe you can take email addresses from ConfTool, because again, one of the main purposes of participating in conferences is not just to read papers and attending presentations, but to strengthen the network and bring this community ahead. And this is my, of course, best wish. I would then bring this session to a closure, not before thanking again Fanica for the excellent support. Enjoy the last session after this one, and then the closing. And see you hopefully on site at ISED or any other conference before that.
Thank you very much. Goodbye.
Thank you so much. Good
Thank you very much.
discussion.